This is section 6.3, and we're going to be graphing radical functions. So what is a radical? It's a square root, it's a cube root, a fourth root, a fifth root. But on this section, we're only going to be graphing square root functions. Let's jump right into the handout, and let's begin on the part that it says, note section 6.3, square root functions, graph the parent graph of all square root functions, which is y equals square root of x. So this guy right here is the parent graph of all square root functions, and let's graph it. So to graph this guy using an input-output table, you simply plug in values that are nice, right? Any graph is a collection of inputs and outputs. You could plug in any numbers you want. I could plug in 0. Think about that. Plugging in 0 right here, the square root of 0 is 0. I could plug in 1. That's nice, because when I plug in 1, the square root of 1 is 1. Could I plug in a 2? I mean, I could, but I'll get a decimal, and that's not that nice when you're graphing by hand. Or a 3, but if I plug in a 4, that's nice, because the square root of 4 is 2. You could also plug in a 9, the square root of 9 is 3. You could keep going. The square root of 16 is 4, the square root of 25 is 5, the square root of 36 is 6. But obviously, on a 10 by 10 graph, you're only going to be using all the way to right here, 9, 3. Okay? Let's graph it. 0, 0, 1, 1, 4, 2, 9, 3. So this is the parent graph. You know, I want to use yellow. This is the parent graph, and let's talk about domain and range on this parent graph. Do you guys remember domain? Yeah. What is the domain of this parent graph? X is greater than or equal to 0. And see, the reason why it doesn't exist over here is because if you plugged in any negative number for x, like let's say you did -1, the square root of -1 is imaginary. And this is not a complex plane with imaginary numbers. It's a real plane with real x values, real y values. So it really does begin right here at the origin 0, 0. It doesn't exist anywhere over here on the left side. So it's at 0 and to the right, that is greater than or equal to 0. Let's talk about range. What's the range?
Y is greater than or equal to 0.
Y is greater than or equal to 0. Perfect. Because the y value, the graph does exist at the y value of 0 and above, so greater than or equal to 0. All right, cool. Now, let's take a look at this next one and graph it quickly using the same method, input-output table. Let's plug in numbers that work out nicely, like square root of 0 is 0, but with a negative in front, it's going to be a -0, which is still 0. The square root of 1 is 1, but with a negative in front, it's going to be what? -1. The square root of 4 is 2, but with the negative in front. The square root of 9 is 3, but with the negative in the front. And let's graph this guy. 0, 0, 1, -1, 4, -2, and 9, -3. As you can see, this is your new graph. So what could you tell me comparing the first parent graph to this new one? They reflect over the x-axis. That's right. It reflects over the x-axis. And that's what I wanted you guys to conclude. I hope you remember that on a parabola, y equals x squared, that would be a U-shaped curve opening up. But if you put a negative in front of the parabola, it would open down. It's the same exact reasoning here. The negative in the front causes a reflection over the x-axis, okay? And we're going to pick up on a lot of more things. Yes. So on this one, again, you could plug in 0, but when you plug in 0, the square root of 0 is 0, and then you take away 2, so you'd have an output of -2. And then I could plug in 1, the square root of 1 is 1, but then you take away 2, what do you get? -1. I could do the square root of 4, that's 2, but take away 2 gives you 0. The square root of 9 is 3, but take away 2 gives you a 1. So let's graph this and see what it looks like. 0, -2 is right here. 1, -1 is right there. 4, 0 is right there, and 9, 1 is right there. So what if we compared this one to the parent graph y equals square root of x? That was the first one up there. It got shifted 2 units lower, right? See, the original one had the square root of 0, 0. It had the square root of 1 is 1. It had the square root of 4 is 2. And it had the square root of 9 is 3. So here's your original one. Wait, I messed up on that one. That dot should have been right here. Scratch that. Okay, I probably shouldn't have drawn the parent graph, but anyway, I wanted to show you that the original parent graph was right here, and it got shifted 2 units down. And the reason why it got shifted 2 units down is because of this minus 2 that's on the outside of the square root.
So if it was a plus 2, it'd just go up?
It would, yeah, if it were a plus 2 on the outside of the square root, it would have gotten shifted 2 units up. That's a great conclusion. That is fact. This is technically our k value. You guys remember square root parabolas? When we had the k value on the outside of the parentheses, it shifts the parabola up and down. It's the same thing here. A negative 2 causes it to shift 2 down. If it were a plus 2, it would have shifted 2 up with the same exact graph. What if I were to graph this guy right here? I want to do this one in red. Input output table. I could do the square root of 0. The square root of 0, sorry about that. The square root of 0 is 0 times 2 is still 0. The square root of 1 is 1, but times 2 will give me 2. Right? When I plug in a 1, the square root of 1 is 1, times 2 will give me 2. What else should I plug in? 4. The square root of 4 is 2 times 2 takes me back to 4. Next number to plug in? 9. Because the square root of 9 is 3 times 2 gives me what? 6. So let's graph these coordinates 0, 0, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, and 9, 6. What happened with this one visually compared to the original parent graph y equals the square root of x? It got up higher. In other words, actually, I'll draw it real quick. Hold on. So I just sketched the parent graph right here. And I did it quickly because I could just think like the input 0, the square root of 0, 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So I could quickly draw the parent graph. And as you could see, the 2 out in the front caused it to get vertically stretched. By 2. If you think about it, the y value here was 1, the y value here is 2, got doubled. The y value here is 2, the y value here is 4, it got doubled. So it got vertically stretched by 2. What do you think is going to happen when I graph this guy right here? It's going to get compressed by 2. It's going to get divided by 2, right? It's going to get compressed by 2. So again, I could plug in 0. The square root of 0 is 0 times half is still 0. When I plug in a 1, the square root of 1 is 1 times half is 1 half. I could plug in a 4, the square root of 4 is 2 times 1 half is 1. Then I could plug in a 9, the square root, right, when I plug in a 9 right there, the square root of 9 is 3, and 3 times half is what? 1.5. Okay, so let's graph the blue one now. 0, 0, still there at the origin. 1 on the x halfway up is right there. 4 on the x half, and then up 1 is right there. 9 on the x, 1.5 would be right there. So this is definitely a compressed version of the parent graph. So the reason why I'm doing all these exercises here with an input-output table, it's not to waste your time. It's so you guys could start concluding that the A value causes a vertical stretch or a vertical compression. Also, the K value, it shifts up or it shifts down. The H value is a left and right shift. Let's actually take a pause right here from this worksheet. You guys could just relax because you don't have this. I want to graph this guy that says y equals parentheses x plus 2 squared plus 1. That's back when we graphed parabolas in semester 1. And we needed to know this back then. Y equals a parentheses x minus h close parentheses squared plus k. Do you guys remember that?
Yeah.
Okay, so how would we graph this parabola by hand back then in semester 1? How would we graph it? We would identify the most important point. What's the most important point? And what is that vertex? -2, comma 1. Okay, so let's go to -2, comma 1. Put a dot right there. And then, do you guys remember what we would do next to graph to get coordinates for that parabola? I mean, we could have used an input-output table and plugged in numbers for x, pulled out numbers for y. But what do we memorize to help us graph parabolas? 1, 1, 2, 4, 3, 9. The pattern 1, 1, 2, 4, 3, 9. So from this vertex, we would go 1 over, 1 up. And we put a dot right there. Then we go back to the vertex, go 2 over, 1, 2, 3, 4 up. And you put a dot right there. Whoops, sorry, right there. Let me erase that. And then go back to the vertex and go 3 over, 1, 2, 3, and 9 up. That would be way up here on the edge. And then we would map them over to the other side of the axis of symmetry, giving us this perfect parabola. You guys remember that? Now, I hope we remember where we got the pattern 1, 1, 2, 4, 3, 9. Does anybody remember where we got that pattern from? We got that pattern from the parent graph. From the parent graph, y equals x squared. Remember, if I plug in a 1 right there, 1 squared is 1. 2 squared is 4. 3 squared is 9. And that's where we got that pattern. All we needed to do is find the HK and then use that pattern, of course, if your A value is 1. If your A value is something else, you'd have to modify the outputs of your pattern. Now, what I want to do is relate this old knowledge to this new knowledge and graph it in the same way. Check it out. So let's go back to this worksheet. And this guy right here, what is the most important point of this square root function? What was the most important point of a parabola? The HK. It's the same deal here. What's the most important point here? The HK. But what is the HK? Okay. The vertex of a parabola. This is not a parabola, but what is the coordinate HK? -2, -3. So H is -2, K is -3. That is the most important point of a parabola. That's the most important point of a square root function. Okay, so let's go to -2, -1, 2, 3. Put a dot right there. Okay. Now, how does the original parent graph work? It actually has a pattern. The original parent graph, y equals square root of x. And you don't have to memorize the pattern, but think about it. The square root of 0 is 0. So it would just stay right there, right? And then the square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. I just did that sketch. You don't have to do that sketch. But there is a pattern right there in the parent graph. It's the square root of 1 is 1. The square root of 4 is 2. Square root of 9 is 3. So the A value is 1. Right here, the A value is 1. So it's going to be the same exact graph with the same exact pattern. Think about it this way. The square root of 1 is 1. So you'd put a dot right here. The square root of 4, so go 1, 2, 3, 4 is 2. So from that beginning point, HK, go 4 over and 2 up and put a dot right there. And then go back to the beginning point and go 9 over 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 3 up, and you'll be right there at the x-axis itself. And that's your graph right there, without doing any math. It's pretty crazy, right? Now, if you're like, oh man, I'm not getting this graphing, I'm not good at graphing, it's okay, you could use Desmos at the end of it all. But the more we practice right here, graphing by hand, the easier we'll be able to understand actual graphs when we look at equations. So this one obviously didn't get reflected over the x-axis. It didn't get vertically stretched or compressed. It only shifted 2 to the left and 3 down. That's why here's the original. All of the points got shifted 2 to the left and 3 down. 2 to the left and 3 down, 2 to the left, 3 down, 2 to the left and 3 down, right? Did I have to do it this way with the pattern? No. I could have, if I wanted to, gone with your traditional input-output table, right? You could plug in a number, any number you want, but 0 is not going to cut it this time because 0 plus 2 is 2, and the square root of 2 is a crazy decimal. So maybe like a -2, that would be nice, because -2 plus 2 is 0. The square root of 0 is 0, and then -3, that'd be a -3. That'd be your output, and there'd be a coordinate, but look how long that took, and that's just to give me the coordinate -2, -3, right? So you could use an input-output table. You know what, I'm just going to continue. I want to plug in a -1. Why am I plugging in a -1? Because I know that -1 plus 2 is 1, and I could do the square root of 1. The square root of 1 is 1, and then 1 minus 3 is -2. But you see, we already have the coordinate -1, -2. -1, -2 is right there. Okay, so it's a lot easier to understand the parent graph, the pattern of the parent graph. The square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. And you could use that pattern, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, to get your new quick graph. Or you could go with your traditional plugging in and pulling out. Like if I wanted to plug in another nice number, what nice number would work that if I add 2 to it will give me a perfect square number? Somebody said 2, right? I could plug in a 2. That'll make this a 4, and the square root of 4 is 2, and 2 take away 3 is -1. So if you go to 2, -1, you get to that point anyway. So you see, this takes a really long time. We could have used the pattern with the parent graph, right? So I hope this makes sense. Let's see. Where is my beginning point? What's my most important point right here? HK. What is that HK coordinate? 1, 0. Remember, think opposite on H. Take K for what it is. There is no K, so K is 0. So let's go to 1, 0. Put a dot right there. Now, I could go to my traditional input-output table, or I could use the pattern of the y equals square root of x, the parent graph. And what is that pattern? If I plug in a 1, what's the square root of 1? 1. So from here, I could go over 1, up 1, right? And put a dot right there. Then I could go back to the HK point, the beginning point, and plug in a 4. The square root of 4 is 2. So 4, 1, 2, 3, 4, 1, 2. And then you could go square root of 9 is 3, and you'd get to that coordinate right there. And voila, it's done. Okay? You didn't have to use the pattern. What is the pattern? It's 1, 1, 4, 2, 9, 3. It's technically the pattern that we use for parabolas, but backwards. It's 1, 1, 2, 4, 3, 9 for parabolas. Right here, it's 1, 1, 4, 2, 9, 3. It's flipped. Okay? So once you get really comfortable with this notation down here, I mean, ultimately, this is what we want to conclude. We want to conclude that we understand this. It's exactly like the vertex form of a parabola. And whenever I write vertex form or this radical function form, I always draw the a value in blue. That a value tells you two things. Does it get reflected over the x-axis? And also, does it get vertically stretched or compressed? You also have the h value, which is the shift from the parent graph to your new graph, left or right. And you obviously think opposite of what you see because of the minus sign. And that's only when it's in an equation. That's when you think opposite on h. And the k value, you take it for what it is, the plus k. That's your shift up or down, okay? So once you get really comfortable with this stuff, you're going to be able to take a multiple choice test and just get the right answer without doing any math. Check it out. So I already graphed this on Desmos. And I want you guys to give me a description of what this looks like. Like, for example, I know that my parent graph, y equals the square root of x, that starts at 0, 0, and then the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, right? So 1, 1, 4, 2, 9, 3. That's a parent graph. But this guy, obviously what happens? The first transformation, the negative, what does it cause? a reflection over the x-axis. So these yellow dots right here would become these red dots down here, right? Opening down instead of up. And then, what else do we know? That this A value of 3, what does that cause it to do? A vertical compression or stretch? Vertical stretch, right? A compression would be a fraction that's less than 1. And if you're thinking, oh, what negative 3 is less than 1. The negative just means that it gets reflected over the x-axis. But now we're going to stretch it by 3, which means that it gets stretched. It gets stretched. This will get stretched. So our new points would be something, or our new graph would be something like that, right? What else? The next value is an H shift 2 to the left and K shift of 6 up. So if I did shift this guy 2 to the left and 6 up, it would be up here at the coordinate negative 2, 6, and it'd be like that. So that is what our graph looks like. Let's check it out on Desmos. Look at it. There it is. It's exactly what we sketched. It starts off at negative 2, 6. It did get vertically stretched. Now, if it would have been just a negative 1, then your next coordinate should be down 1 over 1. If your A value was negative 2, it'd be down 2 over 1. But this A value was negative 3, so it's down 3 over 1. Okay? So we could get very, very accurate just by understanding the A, the H, and the K on any square root function. By the way, what's the domain on this guy? Yes. X is greater than or equal to negative 2. That's great. And how about the range? Y is less than or equal to positive 6. That's right. I think we got it. So we're going to continue with this worksheet. There's more questions on the back. You could use any method you like. You could technically use an input-output table on all of them, even though that takes a long while. You could use the pattern of your parent graph. You could even use Desmos if you really wanted to. So you could see and get used to all the different transformations that happen from the original parent graph to your new graph. Okay? We'll pick up with this tomorrow.